So far, we have gone through quite a number of examples dealing with the same column, having the same specifications and details that are subjected to different conditions, whether the column is short or slender, brace or unbrace, and whether the moment is acting on the major or the minor axis. Assuming that there will always be moment acting onto the column, either in the major axis or the minor axis, or even in both axes. There will be at least 9 loop cases for the columns, as demonstrated in the diagram here. In fact, the short column can be braced or unbraced, since the calculations of the MED will be universal for braced and unbraced short column. We will consider braced and unbraced short columns to be of the same category. For the 4 question examples that we did, it is sufficient to cover most of the column, except those dealing with the moment at the both axes. You may look into the previous calculation steps and observe the unique procedures to design the column of different cases. If you find difficulty to observe the pattern in terms of the calculation steps, this video is produced to help you sort them out. We will leave the design for the double axis later, since we haven't discussed about the relevant design examples. As far as this video is concerned, let us go with the short column with the moment acting in the major and minor axis, slender brace column, major minor axis, and slender unbraced column, major and minor axis. Here we're going to highlight the differences. You may look at these 3 categories: short regardless brace or unbrace, slender, brace, and slender, unbrace. The main differences between the 2 categories, it will be the calculations of the MED. Short columns only involve the first order moment, whereas slender column there will be second order moment. The calculations of the MED differs between the brace and unbraced structure. The calculations for the short column, it will be relatively straightforward. You only need to get the moment acting onto the column plus the moment due to the imperfections. The calculations for the slender column, it will be more tedious, since on top of the first order moment, you will need to calculate the second order moment. However, this second order moment, specifically the M2 here, is calculated on basis of we know the amount of reinforcement bar in the column. That brings you the first round of calculations of the M2. Since you don't know the amount of reinforcement in the column, it is not decided yet, then we will assume this KR, correction factors, equals to 1.0. This will lead to the assumed M2 for you to work out the MED as a start. Use the MED and refers to the column design chart. You work out the AS required. Only then you know the AS. Then you're going to substitute the AS into the equations for you to compute the M2. You're going to repeat the process again to get the MED and then find the AS from the design chart in order to see the assumed value of KR to be more or less the same as the calculated KR. Only then you can confirm the M2. Then you get the finalized MED and then work out the AS required. If you find this difficult to imagine, maybe you can refer to the flow chart here. Short column more straightforward. Your MED is determined by first order moment. Based on the MED calculated, substitute into the equations. Use the column chart to find the AS FYK divided by BH FCK. Those values are known as AS. Use the value obtained from the chart to find your AS. This finishes the design process. Now, in the case that you're dealing with the slender column, there will be second order moment. We will start with assuming K equals to 1, find the assumed N2, and subsequently the assumed MED. Use this MED into the chart here, and then find the AS. Use this AS, go back here to compute the KR. You're going to compare this KR with the assumed value. Now, if the KR is the same, then you know that this MED it will be the same as this. Then the AS here, it will be the finalized AS. Now, if you find the KR here is not the same as the one that you have assumed, that will lead to you another M2. Due to the change in terms of the M2, it will give you the new MED. Use the new MED, substitute into the equations, get the result from the chart, and then find your AS. Go back to the AS required. And then adopt this AS back to the equations to the KR. See if the new KR is consistent with the previous KR. You're going to loop this process until it reaches to a constant stage. That means when you reach to this more or less constant MED, then you may stop the process. The finalized AS shall be the one that provided to the column. You might want to ask, why do you have to go through this process looping until constant? What if I choose not to loop the process? Straight away end at this process without checking the KR. Can I straight away use this AS? The answer is yes. You can try the example which we have mentioned in our reinforced concrete 2 in terms of the slender column. The process of looping this will make the design of AS more economical. Now, if you choose to stop here without going through this looping process, it is okay. But you're going to provide more reinforcement bar than what is required. The structure will still be safe. Just that you have to make sure that the amount of reinforcement bar provided shall not exceed the maximum bar area. But if you see the example that we did previously, due to the loadings are relatively low, the calculated AR that we found it will be consistent with the assumed KR. Therefore, no matter how many times you loop, it will still end up to be the same MED and also the same AS. This brings you another idea that when you see relatively high loading acting onto the column, with respect to the cross-sectional area of the column, you might going to expect some looping process here. So it is okay if you just stop here without looping. The design it will be relatively conservative. If you choose to loop the process, you will see the M2 reduce gradually until you reach to a more or less constant MED. Then the amount of reinforcement bar provided shall be confirmed. This establishes the different calculation steps due to different classifications of the column. Among these classifications of the column, so far we have dealt with only uniaxial bending moment. The moment may be acting on the major or at the minor axis of the column. Dealing with the major axis and the minor axis moment, you will need to be careful on one thing. That means dealing with the dimensions of the column. For all equations with h, if you deal with the major axis, that means you deal with the larger dimensions of the column, which in the 4 example here, if you are dealing with the major axis, your h will be equals to 300 mm. Now if the moment is acting on the minor axis, all the equations with the h shall be taken as the smaller dimensions of the column, which in the case here, the h it will be equals to 150. Having this sorted out, the design of column does not seem to be complicated, although there are so many categories of the columns. But it comes down to only 2 rules: the process to get the MED, and then the dimensions that you are referring from the column's cross-section. We will come back and discuss about the both axis design after we have done the relevant example. Maybe you can challenge yourself after understanding this, and also based on your prior understanding in terms of the process to design and check for the biaxial bending column, which we discussed about this in the module Reinforced Concrete 2. See if you can work out a mechanism to differentiate the design process on the both axes and obeying the principles here. Try it. It's going to be quite interesting.